Welcome back to QHSE Talks. Imagine walking onto a heavy construction site,
Oh yeah, the environment is always chaotic.
Right, exactly. So you look down and you see like a frayed wire on a power tool.
A classic hazard.
Yeah, the copper is exposed, the casing is cracked. I mean, you know immediately it's a hazard. You lock it out, you tag it out, you throw it in the bin.
That's very binary.
It is. It's a clean binary diagnosis. Safe or unsafe. And, we are wired to look for these tangible physical threats. But what if the deadliest hazard on that site is basically completely invisible?
That's the scary part, honestly.
It really is. What if it is hiding in plain sight, just buried inside some massive spreadsheet of average incident reports or daily temperature readings?
And people just gloss right over it.
Exactly. So today, we are taking a stack of your safety study materials and uncovering how the most dangerous things in your facility aren't the ones you can see, but the ones you fail to mathematically anticipate.
Right. The statistical hazard.
Yeah. We are dedicating this highly requested, custom-tailored session of QHSE Talks directly to you, the safety professional striving to master ASP 11 Domain 1 Topic 11, which is, of course, calculating descriptive statistics.
Which is such a massive topic for the exam.
It's huge, and our mission today is to prove that mastering central tendency, variability, probability, and, standard deviation, it isn't just about passing a math test. It is about developing a literal X-ray vision for risk.
I love that framing, actually, because that is the ultimate goal of the safety profession.
Yeah, absolutely.
When we talk about descriptive statistics and safety management, these numbers are never just abstract digits floating on a whiteboard somewhere.
No, they mean something.
They're a proxy for reality. I mean, they represent actual workplace injuries, near misses, catastrophic system failures, and frankly, human lives.
That's a heavy way to look at it, but it's true.
It is. The formulas we are going to explore today allow managers to take a really chaotic, muddy landscape of information and basically filter it down into actionable truth.
Because without it, you're just guessing.
Exactly. Statistics are what allow you to see the hazard when the wire isn't obviously frayed. When the machine sounds perfectly fine, but is, mathematically speaking, guaranteed to fail within the week.
Wow. Okay, that concept, taking an overwhelming mountain of data and distilling it into a single, sharp insight, that's basically a superpower.
It really is.
So let's lay out the roadmap for our journey on this QHSE Talks. We're going to start with the foundational concepts of central tendency, which is how we find the middle of our data.
Right, the basics.
But because the middle often lies to us, we will move into understanding data variability and standard deviation.
This is where things get really interesting.
Yeah, and from there, we will explore the normal distribution, also known as the bell curve, and calculate specific z-scores and probabilities to map out exactly where the danger lies.
Crucial for the exam, yeah.
Very crucial. And finally, we will look at correlation and system reliability, basically proving mathematically whether our safety programs are actually working or if we are, just getting lucky.
It is a really comprehensive journey. And the Associate Safety Professional exam expects you to not just memorize these formulas, but to actually understand the philosophy behind them.
Right. They don't just want human calculator.
No, not at all. The exam doesn't just want to know if you can crunch a number. It wants to know if you understand what that number is screaming at you to do.
Okay, let's start listening to those numbers then. We are looking at the foundations of central tendency first.
Let's do it.
Based on the text, let's just define descriptive statistics right out of the gate. It is the study of obtaining meaningful information by analyzing data from experiments or observations.
That's how we find the center. Right?
Yeah, the center or the anchor of our data. And the most common way we do that is with the mean, which most people just, call the average.
Right, the average. Mathematically speaking, the mean is the balancing point of your data.
Okay, the balancing point.
Yeah, so the formal formula represents this as mu, the Greek letter, which equals the sum of all values in a data set divided by the total number of values.
Mu equals sum over n, basically.
Exactly. If we think about this visually, imagine a seesaw. The mean is the exact spot where you place the fulcrum so that the board balances perfectly, regardless of how the weights are distributed on either side.
I like that visual. So we're taking the total weight, just the sum of everything, and dividing it by the number of objects on the board.
Yep, that's it.
Let's ground this in a real-world safety scenario from the study materials. Let's look at weight calculations, which are, critical when you're determining structural loads for scaffolding or, like, fall protection limits.
Very common exam scenario.
Right. So you have 4 persons on a crew. Their weights are 125 pounds, 173 pounds, 108 pounds, and 211 pounds.
Okay, so the process here is straightforward, but the implications are massive. First, you sum the values to find the total load on that scaffold.
So we just add them all up?
Right. Adding those 4 weights together gives us a total of 617 pounds. To find the mean weight per worker, we basically divide that total by our number of workers, which is 4.
Okay, wait, I'm looking at my notes from the source text here, and this actually highlights a great lesson for anyone studying for the ASP.
Oh, the typo.
Yeah, the text provided to us explicitly states that 617 divided by 4 equals 126.75, or roughly 127 pounds.
Right.
But like any basic calculator will tell you that 617 divided by 4 is mathematically 154.25. The study material literally contains a typo.
Which is honestly a brilliant accidental lesson for candidates.
How so?
Well, as safety professionals and as exam takers, you will occasionally encounter study materials or even real-world engineering specs that just have typos.
That's terrifying but true.
Yeah, you cannot blindly trust a printed number if it defies the fundamental process. The process is the anchor, right? The sum of the data divided by the n value.
So stick to the formula.
Exactly. If the exam asks you to calculate it, trust the process and trust your calculator, not necessarily a flawed practice question.
Trust your calculator. Good advice. Okay, so if the true mean is 154 pounds, that gives us our mathematical center.
Right.
But if I am a safety manager, knowing the average weight of my crew is 154 pounds doesn't really help me if I have a harness rated for only 150 pounds.
No, it doesn't help at all.
Right. I mean, the 108-pound worker is fine, but the 211-pound worker is in lethal danger, even though the quote-unquote average says everything is mathematically copacetic.
And that gets to the absolute heart of the issue with the mean. The mean is heavily influenced and sometimes completely distorted by extreme values.
It just hides the individual reality.
Exactly. This is why we have other measures of central tendency, like the mode.
The mode.
Yeah, the mode is simply the value that appears most frequently in a data set.
Let's apply that to a safety environment then. If we look at a set of safety training exam scores from the text, we have 95, 88, 86, 88, and 90.
Okay, so just scanning that list, the number 88 appears twice. Right, while all the other numbers only appear once.
So the mode is 88.
Exactly. Let's scale that up to a larger data set from the text. We have 1, 3, 6, 6, 6, 6, 7, 7, 12, 12, 17.
Okay, so a lot of 6s there.
Yeah, the number 6 appears 4 times, which is more frequent than any other number, so the mode is 6.
Right.
And for the exam, it's important to remember that if multiple values tie for the highest frequency, the data set is basically considered multimodal.
Okay, so if I'm tracking daily near-miss reports and the number of reports per day over a week is like 2, 5, 2, 5, and 1, my data set is multimodal with modes of 2 and 5.
Spot on.
But why do I care? Like, what is the mode telling me that the mean isn't?
Well, the mode acts as a symptom tracker. Think about injury logs.
Yeah.
If you calculate the mean of your injury costs, a single multi-million-dollar explosion will make your average daily injury cost look astronomically high.
Yeah, it skews everything.
But if you look at the mode of your injury types, you might find that, say, laceration to the left index finger is your mode. It is the most frequent occurrence.
Oh, I see.
Right. As a safety manager, you don't necessarily care about the average injury in that moment. You care that a specific preventable event is happening repeatedly. The mode points a giant red arrow at your most common, recurring systemic failure.
Wow, okay. So the mean gives us the mathematical balance, but the mode gives us the operational reality of what's breaking most often.
Exactly.
And that brings us to the third measure, which is the median. This one is defined as the middle value in the list of data when that data is arranged in numerical order.
Right. So if you have 5 numbers ordered smallest to largest, the median is just the third number.
Right in the middle.
Yeah. If you have an even number of data points, say 6 numbers, you take the 2 middle numbers, add them together, and basically divide by 2.
Okay, so why do we need this one? If we have the mean for balance and the mode for frequency, what is the median really doing for us?
The median is your insulator against outliers.
Insulator, okay.
Yeah, let's go back to that chemical spill example. You have 99 tiny chemical spills that cost $10 each to clean up. And you have one massive spill that costs $10 million. If you take the mean, the average cost of a spill in your facility is over $100,000.
Oh, wow.
Right. If you take that number to the board of directors and say, hey, every time we drop a beaker, it costs us $100,000, they are going to fire you because the mean is lying.
Right, right. The one extreme event pulls the average wildly out of proportion to the daily reality.
Exactly. But if you line up all 100 spills in a numerical order from $10 all the way up to $10 million, and you look at the middle value, the median that value is $10.
So there's 99 $10 spills.
Exactly. The median tells the board a typical everyday spill costs $10, but we have a catastrophic outlier risk we need to insure against.
So it filters the noise.
Yes. The median ignores the noise of the extremes and shows you the true unweighted middle. The ASP exam will absolutely test your ability to know which of these three tools to pull out of your toolbox, depending on the story the data needs to tell.
The mean is the balance. The mode is the frequency. The median is the insulated middle. I love that breakdown.
It's a great way to remember it.
But as we just discussed with the scaffolding weights and the chemical spills, simply knowing the middle of the data can be kind of a dangerous trap.
It really can.
Which bridges our conversation directly into the concept of data spread. If central tendency tells us where the anchor is dropped, variability tells us how far the boat can drift away from that anchor.
That drift is what we call variance. The formal definition from our text is that variance is the degree to which the variables in the dataset are spread out away from the mean.
Let's talk about why variance is so critical to safety before we get into the heavy math.
Okay, sure.
If I tell you the average daily temperature in my factory is 70 degrees Fahrenheit, that sounds like a perfectly safe, comfortable working environment.
Sounds ideal.
But what if the temperature swings from 140 degrees during the day to 0 degrees at night?
Well, that's a nightmare.
Right. But the average is still exactly 70 degrees. But the variance is massive. If I only look at the mean, I think my workers are fine. If I look at the variance, I realize that they are suffering from heat stroke at noon and hypothermia at midnight.
That is a perfect analogy. The average is lying to you, and the variance is telling you the truth.
Yeah.
In safety engineering, a high variance basically means your process is fundamentally out of control. Let's look at the mathematical mechanics of how we capture that chaos, though.
Okay, let's get into it.
The text outlines a vital rule for finding variance. To find it, we must calculate the distance of each individual data point from the mean, and then we must square that result.
Okay, this is where I want to push back a little because this always tripped me up in statistics class.
It trips everyone up, don't worry.
Why are we squaring the distance? Like if the mean is 10 and my data point is 5, the distance is 5. If my data point is 15, the distance is 5. Why can't I just add up all the distances to see how far away everything is?
Okay, let's play that out. If the mean is 10 and your data point is 5, the true mathematical distance is -5 because you are below the mean.
Okay.
If your other data point is 15, the distance is +5. If you simply add -5 and +5 together, you get 0.
Ah, I see. The negative and positive distances just cancel each other out.
They mathematically neutralize each other. If you just added the raw distances, a wildly out-of-control system swinging from 0 to 100 would show a spread of 0 because the extremes just balance out.
That makes total sense.
So by squaring the distances, every single value becomes a positive number. -5 squared is +25, +5 squared is +25.
Right.
Squaring the numbers acts as an absolute value mechanism that heavily penalizes data points the further they get from the mean.
So it basically creates a massive mathematical red flag for outliers.
Exactly.
If a point is 2 units away, it adds 4 to our variance. But if it's 10 units away, it adds 100. It amplifies the danger of extreme swings.
Let's visualize the geometry of this with the text's example of 10 test scores. We have 80, 85, 90, 75, 95, 85, 80, 85, 90, and 85.
Okay, 10 scores.
The first step is to find the mean, which is 85. The second step is to subtract that mean from each score and square the result.
Okay, I'm not going to read every single arithmetic step here because, our listeners know how to subtract.
Right, hopefully.
But conceptually, let's look at the score of 85. 85 minus the mean of 85 is 0. 0 squared is 0.
Yep.
So that data point contributes absolutely nothing to our variance because it is perfectly average. It is exactly on the anchor.
Correct.
But look at the score of 75. 75 minus 85 is -10. Squared, that is 100. The score of 95 is +10. Away from the mean. Squared, it is also 100.
And those two outliers, 75 and 95, are generating the vast majority of the variance in this data set.
Wow, yeah.
The third step is to sum all of those squared deviations, which for this data set equals 300. And the final step for variance is to divide that total sum by the number of scores, which is 10.
So 300 divided by 10 gives us a variance of 30.
Yeah. Exactly.
But wait, if these are test scores and we squared all the differences, our unit of measurement is completely distorted now, right? Like the variance is 30 squared test scores. What does a squared test score even mean? Or if we were measuring factory temperature, what is a squared degree?
It means absolutely nothing in the physical world. It is purely a mathematical abstraction.
Oh, okay.
And that is exactly why the concept of standard deviation exists. Standard deviation, represented by the Greek letter sigma for a population, or the letter S for a sample, is simply defined as the square root of the variance.
So taking the square root basically undoes the distortion. It strips away the square unit and brings the number back down into the original reality we were measuring.
Exactly. The square root of our variance of 30 is roughly 5.47. So the standard deviation of those test scores is 5.47 points.
Okay, that makes so much more sense.
Right. It tells us, in a language we actually understand, the typical standardized distance that any given score drifted away from the average.
Now, before we apply this, there is a massive trap on the ASP exam regarding standard deviation that we really need to dissect.
Yes.
The formula changes depending on whether you are analyzing a population or a sample.
This is known as Bessel's correction, and it is honestly a critical safety philosophy disguised as a math rule.
How so?
Well, if you are calculating the standard deviation for an entire population, meaning you have absolute godlike knowledge of every single data point that exists, you divide your squared sum by big N, the total number of items, just like we did in our variance example where we divided by 10.
But in the real world of safety management, we almost never have the entire population. I mean, I don't have a data for every single bolt that will ever be manufactured. I only have a sample of 100 bolts that I pulled off the line today.
Exactly. And when you are dealing with a sample, the formula dictates that you divide by little n minus 1 instead of just n.
Okay, I have to challenge this.
Go for it.
By subtracting 1 from the denominator, you are making the number you divide by smaller, which means the final result, the standard deviation, is going to be artificially larger.
Mathematically, yes.
So why are we penalizing the math just because we don't have the whole population? It feels like we are intentionally fudging the data to make the variance look worse than it might actually be.
We aren't fudging it. We're basically building in a margin of statistical safety.
Oh, interesting.
Because we only have a sample. We have to humbly accept that our sample might not perfectly capture the extreme true ends of the entire population.
Right.
We might have missed the absolute worst bolt on the assembly line. So by dividing by n minus 1, we slightly inflate the standard deviation to account for that unknown risk.
That's fascinating.
It is the mathematical equivalent of wearing a belt and suspenders. It ensures we don't underestimate the chaos in our system just because our small sample happened to look somewhat stable.
Wow, okay. The math itself has a safety factor built into it. I love that.
It's pretty elegant.
So if we look at a sample from the SPAN workbook material provided in our sources, the numbers are 10, 10, 15, 25, and 35.
Okay.
To find the sample standard deviation, we find the mean, which is 19. We find the sum of all squared differences from that mean, which gives us 470.
And here's where Bessel's correction kicks in. Because we have 5 numbers in our sample, n is 5, but we divide by n minus 1, which is 4. Yeah. 470 divided by 4 equals 117.5. And then the square root of 117.5 gives us our sample standard deviation of 10.839.
Okay, I want to offer an analogy here to help visualize standard deviation, especially in a manufacturing or safety engineering context.
Please do.
Let's talk about the structural tolerance of bolts being used to build a suspension bridge.
High stakes.
Very. So a data set with a very low standard deviation means every single bolt coming off the assembly line is almost exactly the identical perfect diameter. They all fit perfectly. The process is incredibly tight, incredibly predictable.
The variance is minimal, yeah.
But a high standard deviation means the bolts are coming off the line in wildly different sizes. Some are too thick, some are too thin. Now, the average size of all those bolts might still be the exact specified requirement. The mean looks perfect.
Right.
But if you try to build a bridge with a high standard deviation of bolt sizes, the bridge is going to collapse because half the bolts will snap under pressure and the other half will just slip out of their fittings. High standard deviation means the process is out of control, regardless of what the mean says.
That is a phenomenal way to contextualize it. The standard deviation is the true heartbeat of system reliability.
Yeah.
Now, the SPAN workbook provides a very specific piece of advice for candidates regarding these calculations.
What's that?
Learn to do standard deviation on a modern scientific calculator using the stat function prior to the exam.
Oh, absolutely. Because if you try to do all that squaring, summing, and square rooting by hand for a list of 20 numbers, you're going to burn 20 minutes of exam time. And if you miss one negative sign, the whole answer is shot. You have to understand the theory of Bessel's correction and squared distances, but let the microchip do the heavy lifting on test day.
Absolutely. The manual walkthrough is for your comprehension of the mechanism. The calculator is for your execution on the exam.
Right.
And understanding that standard deviation mechanism leads us to the most famous visual representation of risk in statistics, the normal distribution or the bell curve.
So we take all these measurements, the mean, the variance, the standard deviation, and we plot a massive amount of real-world safety data on a graph. And as if by magic, the data almost always forms this very specific shape.
It is one of the profound mysteries and conveniences of the natural world, honestly.
It really is.
The physical characteristics of the normal distribution are clearly defined in the text. It features a single peak in the direct center, which represents the mean, the median, and the mode all occurring at the exact same spot.
Everything aligns.
Right. It is perfectly symmetrical. Half the data points fall on the left side of the peak and half fall on the right.
And the tails of the curve, the slopes on the far left and far right, they slope downward and extend indefinitely along the horizontal axis.
Yes, indefinitely.
We are going to come back to those tails in a minute because they hold a terrifying reality for safety professionals.
They really do.
But first, let's talk about the area under the curve. The text notes that no matter what the value of the mean is, and no matter how wide or narrow the standard deviation is, the total area under that curve is always exactly 1.00.
That 1.00 basically represents 100% of probabilities. Every possible outcome exists somewhere beneath that curve.
Right.
And because of the natural geometry of this curve, we can apply a foundational statistical constant known as the empirical rule. This is something every ASP candidate must have memorized, burned into their brain.
The 68, 95, 99.7 rule.
Yes. In a perfectly normal distribution, exactly 68% of all data points will fall within one standard deviation of the mean. This means one standard deviation to the left plus one standard deviation to the right.
Okay, so a big chunk right in the middle.
Exactly. If we move further out, 95.45% of the data falls within two standard deviations of the mean, and 99.73% of the data will fall within three standard deviations.
Let's put this into a high-stakes scenario to answer the so what question. Like, why does the safety director care about the geometry of a bell curve?
Okay, let's look at the text framework regarding workplace injuries. Let's say your massive manufacturing company averages 10 recordable injuries per month. You've done the math, and you've calculated your standard deviation to be exactly 2.
Okay, so our mean is 10, our sigma is 2.
By mapping this to the empirical rule, we can instantly define our zones of normalcy, concern, and crisis.
How so?
Well, one standard deviation is 2, so 10 minus 2 is 8, and 10 plus 2 is 12. We can confidently tell the executive board that 68% of the time, roughly 2/3 of the year, we will experience between 8 and 12 injuries.
Right.
That is our operational baseline. That is a cost of doing business with our current safety culture.
So what happens if we have a month with 14 injuries?
We look at the curve. 2 standard deviations would be 2 times 2, which is 4. 10 plus 4 is 14.
Okay.
So 14 injuries puts us exactly at the edge of the 2 standard deviation mark.
Yeah.
The empirical rule tells us that 95.45% of the time, our injuries should fall between 6 and 14. A month with 14 injuries is rare. It only happens a few times a decade by pure chance.
But what if we hit 16 injuries in a month? 3 standard deviations out is 10 plus 6, which is 16. The rule says 99.73% of our data should be below 16. So if we hit 16 or 17 injuries, the statistics are screaming at us.
That is the power of the curve.
Yeah.
If you hit 17 injuries, you don't just chalk it up to a run of bad luck.
No.
The math proves that a 17 injury month is so far outside the standard variance of your system that your system itself must have fundamentally broken.
Something changed.
Exactly. A new, unaccounted for variable has entered the facility. Maybe a new piece of heavy machinery was installed without proper training, or a specific supervisor is actively overriding safety protocols. The bell curve tells you that a 17-injury month is not random variance. It is a systemic failure requiring immediate aggressive intervention.
Man, let's talk about those tails of the curve again. The text explicitly states that the tails extend indefinitely and never actually touch the horizontal axis.
Right, the asymptotes.
Yeah, the curve gets infinitely close to zero probability, but it never reaches absolute zero. Doesn't that imply, mathematically, that no matter how many standard deviations away an event is, there is always a non-zero chance of an extreme apocalyptic safety event happening?
It absolutely implies that. And this is the concept of the black swan event.
Black swan, right.
It is a mathematical reality that validates the entire profession of safety engineering. Even if a catastrophic blowout is 6 standard deviations away from the mean, making it astronomically rare, like a once-in-a-century probability never hits zero.
Because if the probability ever hit zero, we wouldn't need secondary containment vessels. We wouldn't need redundant emergency shutdown valves.
Exactly.
But the human brain is terrible at conceptualizing a 5 or 6 standard deviation event. We assume highly unlikely just means impossible.
But impossible is not a statistical term. The history of industrial disasters, from the Challenger space shuttle to Deepwater Horizon, is essentially a history of organizations looking at the extreme tail of a probability curve and assuming it was zero.
Wow.
The normal distribution curve allows us to map exactly how rare an incident is, but the asymptotes, the tails never touching the axis, they are a permanent warning that, given enough time, the incredibly rare will inevitably occur.
That is a chilling but vital perspective. We have to engineer for the tails.
We have to.
Now, the empirical rule is great for mapping data that falls cleanly onto exactly 1, 2, or 3 standard deviations. But reality's messy. What if we want to know the probability of an event that falls somewhere in between, say like 1.3 standard deviations away?
That brings us to z-scores and how we navigate exact probabilities on the exam.
Okay, let's get into z-scores.
A z-score is basically the tool we use to find the exact area under the normal curve for any arbitrary data point.
Yeah.
It translates a real-world measurement into a standardized metric.
Okay.
The z-score tells you, to the decimal point, exactly how many standard deviations a specific value is from the mean.
And the formula for the z-score is straightforward. It's z equals x minus mu divided by sigma.
Right.
Or, in plain English. You take your specific data point, subtract the average, and divide that result by the standard deviation. Let's walk through a complex test score scenario directly from the source material, because this highlights how exam writers really try to trap candidates spatially.
That's a great idea. Imagine 300 people took the CST exam, the mean score was 115, and the standard deviation was 15.8.
Okay, got it.
And you passed the exam with a score of 139. The question asks, out of those 300 people, how many scored higher than you?
Okay, so we need to map our spatial location on the curve. Step 1 is calculating our z-score. Our specific score, x, is 139. The mean, mu, is 115.
Right.
So 139 minus 115 gives us a raw distance of 24 points above average.
Exactly.
Now we divide that distance by our standard deviation of 15.8. So 24 divided by 15.8 equals a z-score of roughly 1.52.
So we are 1.52 standard deviations above the mean. Now on the exam, you'll be provided with a standard normal probability table. You look up a z-score of 1.52.
Right, in the table.
The table will provide you with the area under the curve between the mean and your z-score. According to the text table, 1.52 corresponds to an area of 0.4357.
But here's where the spatial awareness really kicks in. 0.4357 is not our final answer. That number only represents the slice of the curve from the exact middle, the score of 115, up to our score of 139.
That's a common mistake people make.
Yeah, but the question asks how many people scored higher than us. Before we can answer that, we have to account for everyone who scored below average.
Because the bell curve is perfectly symmetrical, the entire left half of the curve, everyone who scored below 115, represents exactly 50% of the data, or 0.5.
Okay.
To find out what percentage of the total test takers scored lower than you, we must add that entire left half to the slice we just found. 0.5 plus 0.4357 equals a total area of 0.9357.
So 0.9357, or 93.57% of the entire curve, sits behind our score. But the exam question is tricky. It doesn't ask who scored lower. It asks how many people scored higher. We want the area in the extreme right tail past our score.
Since the total area of the curve is always exactly 1, we subtract the area behind us from 1. 1 minus 0.9357 equals 0.0643.
And the final step is translating that percentage back into real humans. There were 300 people who took the exam. We multiply 300 by 0.0643, which equals roughly 19.29.
Yep.
So out of 300 people, approximately 19 scored higher than you.
That is a phenomenal example of why statistics and safety isn't just plugging numbers into a formula. You really have to mentally visualize where you are standing on the curve, which direction you are looking, and how to combine or subtract areas to find the specific hazard zone you are evaluating.
It's very spatial. Let's try another one that requires working backward. The average test score is 163, and the standard deviation is 24.
So,
The question asks you to estimate the score that represents the 5th percentile. The multiple choice options are 9, 116, 124, and 210.
this is a classic exam strategy question. It tests whether you can use conceptual knowledge to bypass exhaustive table lookups.
Love those.
First, visualize the 5th percentile. It means only 5% of the data is worse and 95% is better. You're standing way down in the left tail of the curve.
So right away, we can look at the options. The mean is 163, which is the 50th percentile. So option 210 is completely out. That's way above average. On the other extreme, option 9 is so low, it's basically almost impossible. 163 minus 9 is a distance of 154 points. With a standard deviation of only 24, a score of 9 is over 6 standard deviations away. That's a statistical absurdity for a test score.
Which leaves us with 116 and 124. We know from the empirical rule that 2 standard deviations below the mean captures roughly the bottom 2.5% of the curve. 1 standard deviation below captures roughly the bottom 16%.
Right.
So the 5th percentile must sit somewhere between 1 and 2 standard deviations below the mean. Specifically, the 5th percentile corresponds to a z-score of about negative 1.64.
So if we take our standard deviation of 24 and multiply it by roughly 1.64, we get a distance of about 39 points.
Correct.
We subtract 39 from our average of 163, and we land at 124.
Exactly. By understanding the physical layout of the curve, you eliminated half the answers instantly and verified the correct answer with a quick approximation rather than getting lost in the weeds of a probability table.
It saves so much time.
Speaking of physical layouts, there is a specific question in the Bowen EHS study material that asks about the purpose of a histogram.
Ah, yeah. A histogram is essentially the blocky bar chart cousin of the smooth bell curve. The correct answer to the question is that a histogram is used to diagram the data distribution.
It is the visual bridge between raw numbers and statistical probability. Before you assume your data fits a perfect normal distribution, you plot it on a histogram.
Right, to see what it looks like.
If the bars form a roughly symmetrical mountain in the middle, you can proceed with z-scores. If the bars are skewed heavily to the left or right, it tells you that the normal distribution rules might not apply and your risk profile is heavily weighted in one direction.
That makes perfect sense. That brings us to our final major topic area: relationships, reliability, and probabilities.
The big leagues.
Yeah. Up until now, we have been examining single data sets in isolation, a list of scores, a list of weights. But safety engineering is fundamentally about causality. We want to know how one variable affects another. Does increasing safety training actually decrease incidents, or are we just wasting money in a classroom?
That is the essence of correlation. The exams require candidates to be familiar with 2 main terms here: the Pearson product moment coefficient of correlation, represented by the letter R, and the Spearman rank order coefficient, represented by the Greek letter rho.
The source text shows the formula for the Pearson coefficient, and honestly, it is a nightmare.
It's intense.
It involves n times the sum of x times y minus the sum of x times the sum of y, all divided by the square root of a massive bracketed equation involving squared sungs. I'm not going to pretend to walk through that verbally.
And you shouldn't. As we discussed with standard deviation, modern statistical software and scientific calculators handle the Pearson formula instantly.
Thank goodness.
The exam is not testing your ability to manually execute 20 interdependent variables without making an arithmetic error. It is testing whether you understand what the resulting coefficient actually means for your safety program.
So let's decode the coefficient. The correlation coefficient will always be a number bounded between negative 1.0 and positive 1.0.
A positive 1.0 indicates a perfect positive correlation. As one variable goes up, the other goes up in lockstep.
Okay.
A negative 1.0 indicates a perfect inverse correlation. As one goes up, the other goes down identically. And a coefficient of exactly 0 means the variables are completely independent. They have absolutely no relationship to each other.
Let's test this with a real-world scenario from the source text regarding behavior-based safety.
Okay, let's hear it.
A safety manager implements a program where employees conduct peer safety observations. The manager wants to know if these observations are actually reducing accidents, so they track the data for 6 months. In January, 15 observations were conducted and 4 near-miss accidents were reported. In February, 20 observations, 6 accidents. In March, observations dropped to 12 and accidents spiked to 10. By June, observations hit a high of 30 and accidents dropped to just 1.
So the exam question asks for the correlation coefficient between observations and accidents, giving multiple choice options like 1.4, 0.7, negative 0.7, and negative 1.4.
Well, we can immediately throw out 1.4 and negative 1.4. The coefficient mathematically cannot exceed 1. It is impossible.
Right, the impossible.
That leaves us with 0.7 and negative 0.7.
Now look at the trend in the data. When observations were low in March, accidents were high. When observations were high in June, accidents were low.
They move opposite.
Exactly. They're moving in opposite directions. That is an inverse relationship. Therefore, the correlation must be negative. The answer is negative 0.7.
Let's debate the so what of this number, though. A negative 0.7 is a fairly strong negative correlation. It looks like great news for the safety manager. They can take this math to the CEO and say, look, the behavior program works. We have mathematical proof that more observations equal fewer accidents.
Right, they look like a hero.
But I have to push back on this as a cynical safety professional. Correlation does not equal causation.
Oh, the golden rule of statistics.
Yeah. If I tell my workers their annual bonus depends on conducting safety observations and having fewer accidents, aren't they just going to conduct a bunch of superficial observations and stop reporting the accidents?
Yep, it happens all the time.
The math will show a beautiful negative 0.7 correlation, but the site itself might actually be getting more dangerous because the culture has become secretive.
That is a brilliant and really necessary pushback. Statistics can only show you the mathematical relationship between the numbers on the page. They cannot measure the integrity of the culture that generated those numbers.
Exactly.
The negative 0.7 proves the variables are moving together. It is up to the human safety professional to investigate why they are moving together. Is it genuine hazard reduction, or is it observation fatigue and underreporting? Statistics are a flashlight in the dark, but they don't replace the need to walk the site and actually talk to the workers.
That is a crucial distinction. The math is a tool, not a savior. Moving from human behavior to machinery, let's look at a much more rigid statistical relationship. Probability of failure versus reliability.
In system engineering, reliability is defined as the ability of a system or component to perform its required functions under stated conditions for a specified period of time. It is expressed as a probability, basically a number between 0 and 1.
The text provides a very simple formula connecting reliability to the probability of failure, which is denoted as P sub F. The formula is probability of failure equals 1 minus reliability.
If a critical pressure valve has a manufacturer reliability rating of 0.88, what is the probability that it fails? We simply subtract 0.88 from 1. The result is 0.12. There is a 12% probability of failure.
That seems almost insultingly simple compared to the z-scores and normal curves we were wrestling with earlier.
It is simple, yeah.
But it drives home a fundamental binary truth in engineering. A component either works or it fails. The probabilities of those two states must always sum up to exactly 100%.
Indeed. But what happens when we want to prove that a new safety intervention is reliable? That brings us to a concept that haunts graduate students and safety professionals alike, p-values and statistical significance.
Oh boy, the p-value. The source text defines it as the probability of obtaining a result as extreme as the one observed, assuming the null hypothesis is true. I'm going to need you to translate that into plain English, because that definition is dense.
Let's break it down using a real scenario. Let's say your company spends $2 million upgrading the ventilation system to reduce respiratory incidents.
A big investment.
Huge. You want to prove the investment worked. In statistical research, you always start with a skeptical baseline called the null hypothesis.
Explain the null hypothesis like I'm an executive who didn't want to spend the $2 million.
Okay, the null hypothesis is the absolute belief that your expensive new ventilation system did absolutely nothing.
Nothing at all.
Right. It assumes that there is zero actual difference in the air quality, and any slight improvement in respiratory health you measure is just random luck. It is the mathematical embodiment of the phrase, nothing special is happening here.
Okay, so the null hypothesis is the villain we have to defeat. We have to prove that our results aren't just a fluke of random variance.
Exactly. When you run your respiratory data through statistical software, it spits out a p-value. The text explicitly focuses on the 0.05 level of significance. This is pretty much the gold standard in most scientific research.
So what does a p-value of 0.05 actually mean?
It means that if the null hypothesis were entirely true, if the ventilation system truly did nothing, there's only a 5% chance that you would see the health improvements you are currently looking at, just by pure random luck.
A 5 in 100 chance that this is a fluke, which means, conversely, we have a 95% confidence level that our intervention actually caused the improvement.
Yes, exactly.
The lower the p-value, the more aggressively we can reject the null hypothesis. We can confidently tell the board, the $2 million worked, and I have the math to prove it.
What you're really pointing out there is the transition from descriptive statistics to inferential statistics. You are inferring a truth about reality based on the significance of the data. And the final piece of the puzzle provided in the text for evaluating outcomes is the binomial distribution.
The formula for this is also quite intimidating. P of x equals n choose x times p to the power of x times q to the power of n minus x.
Without getting bogged down in the algebra, the conceptual utility of the binomial distribution is basically estimating expected outcomes when there are exactly two possibilities: success or failure, pass or fail.
Like inspecting fire extinguishers across a massive campus, every extinguisher either passes the pressure test or it fails. There is no middle ground.
Exactly. If you know the historical probability of failure for a specific brand of extinguisher, the binomial distribution allows you to mathematically predict exactly how many failures you should expect to find during your annual inspection of 500 units.
So it sets a baseline.
It sets the mathematical expectation, yeah. If you find significantly more failures than the binomial distribution predicted, you have a systemic issue, perhaps a bad manufacturing batch or environmental degradation, rather than just random wear and tear.
It all comes back to defining what is normal so we can identify what is dangerous. That perfectly encapsulates our mission today. Let's recap the intense mathematical journey we just took on this QHSE Talks.
We covered a lot.
We really did. We started by seeking the anchor of our data using central tendency. The mean gives us the mathematical balance point, the median protects us from the distortions of catastrophic outliers, and the mode flags our most frequent recurring systemic failures.
But because that center can be deceptive, we explored how data spreads out. We learned why we must square the distances from the mean to heavily penalize extreme outliers, leading us to variance.
Right.
We then used Bessel's correction, subtracting 1 from our sample size, to build a margin of safety into our standard deviation, basically acknowledging the limits of our knowledge.
We took that standard deviation and mapped it onto the normal distribution, the bell curve. We used the 68, 95, 99.7 empirical rule to establish our operational baselines.
And we stared down the tails of that curve.
Yeah, realizing that in statistics, the impossible is merely the incredibly rare, demanding that we engineer defenses against the black swan events.
We learned how to pinpoint exact spatial probabilities on that curve using z-scores, conceptually eliminating wrong answers on the exam by visualizing our location relative to the mean.
And finally, we connected the dots of causality. We used the correlation coefficient to prove the relationship between behaviors and accidents while maintaining the critical human awareness that correlation does not equal causation.
So important.
We defined reliability against the probability of failure. And we used the 0.05 p-value to confidently reject the null hypothesis, mathematically proving the worth of our safety interventions. Mastering these calculations is the absolute key to passing Domain 1 Topic 11 of the ASP exam.
It really is.
But more importantly, it is the key to transforming raw, chaotic numbers into actionable risk control tools.
It equips you with the diagnostic clarity required to navigate the muddy waters of complex systems. It allows you to actually see the invisible hazard.
Which brings me to a final provocative thought for you to ponder. We've spent this entire time exploring how statistical reliability, variance, and standard deviations can predict machine failure and map human injury patterns based on historical data.
Right.
But looking forward, the landscape of data collection is changing exponentially. With the integration of real-time AI monitoring, computer vision, and biometric wearables, safety managers won't be looking at last month's injury logs.
No, they'll have it all instantly.
Right. They will be tracking a worker's physical fatigue and micro-deviations in real time. If an algorithm can instantly spot a half-standard deviation shift in a crane operator's reaction time, how will that change the definition of an acceptable variance in the safety protocols of tomorrow? Will the bell curve of the future be so tight that the margin for human error is mathematically eliminated?
Wow. The tools we use to measure the chaos are evolving, and the expectations placed on safety professionals to interpret that data will honestly only grow more rigorous.
And with that, we wrap up our session. The diagnostic landscape of safety might be inherently murky, filled with latent failures and statistical noise. But with these descriptive statistical tools firmly in your grasp, you have the analytical vision required to see right through it. Keep questioning the mean, respect the variance, and trust the process. We will see you next time on QHSE Talks.